Hi everyone, imagine we can build chiplet systems without using big and power-hungry SerDes. That's what UCIe 2.0 makes possible. Today's star chip, called monolithic SoCs, are hard to make. They cost more, use more power, and often fail during manufacturing. So many companies now use chiplet, smaller chips that work together. But without a common way to connect chiplets, it's not easy to build systems. UCIe 2.0 gives us a standard way to connect chiplets in both 2D and 3D. It's very fast, up to 10.5 terabits per second per millimeter, and uses very little power, less than 0.6 picojoule per bit in a 3nm process. This changes how we build connections. Instead of making very fast SerDes with complex equation, we now focus on making connections that are dense and energy efficient. With UCIe 3D, we go beyond all connection limits. We now get higher bandwidth and better power use. Earlier, UCIe only worked in 2D, and with thicker interpolars, it's also called 2.5D. Now, UCIe 2.0 supports true 3D stacking using hybrid bonding. This bonding makes the bump between chips much closer, down from 45 microns to under 10 microns. This gives us much better performance, up to 10.5 terabits per second per millimeter, even at lower power. But the big change is not just speed. Now, we are limited by how closely we can press the bump, not by the circuits. This means we no longer need very fast lanes. We can use more lanes at moderate speeds and get high bandwidth in a better way. At ICC 2025, a test chip used dynamic power saving and clock gating. It reduced power used from 0.6 to just 0.46 picojoule per bit. So UCIe 3D is good for both speed and power savings. All SerDes was made for long distance, where signals weaken and need help to recover. But UCIe 3D is different. UCIe 3D connects chips very closely, less than 100 microns apart. So we don't need CTOE, FV, or DFE anymore. Now, the focus is on saving power and keeping clock timing stable. At ICC 2025, a 3nm chip showed we don't need complex clock recovery like CDR. Instead, engineers use the simple match delay phase interpreter to keep timing steady, even when power changes. This makes the system more stable and energy efficient. Also, instead of using 64 gigabit per second links, UCIe 3D uses more lanes at 16 to 32 gigabit per second to reach higher total bandwidth. This helps save power and avoid using heavy equation. The test chip shows one-way clock forwarding with match delay works well for stable timing and low power. Now, let's see how UCIe PHYs are designed to save power, keep accurate timing, and send signals clearly. A big challenge is clock synchronization. In all SerDes, PLs and CDRs are used to fix timing noise. But in chiplet, power noise and voltage drops can cause timing problems. At ICC 2025, engineers solved this using a match delay phase interpreter and parent skew correction. This adjusts the timing of each lane in real time and improves the airway stability by 34%. On the transmitter side, the design is simple. UCIe 3D uses low-power inverter-based driver. Wi-Fi ran at 32 gigabit per second and only used 2.2 dB FFE. Just small correction. It used only 0.6 picojoule per bit, and with clock gating, it dropped to 0.46 picojoule per bit. On the receiver side, the change is driven from voltage and temperature changes. The test chip has a self-calibrating receiver with a real-time VT drift correction. With built-in temporary, it could adjust timing during operation. This makes data transfer reliable even when power conditions change. Do this new idea really work? Yes. Lab tests show UCIe 5 have great bandwidth and power efficiency. But testing UCIe 3D is harder than all SerDes because the bump between chiplets are too small to pop directly. So the test chip has a built-in diagnosis. It recorded the timing drift in real time for each lane. This helps engineers find and fix problems fast. It also had a new repair system. Instead of fixing one bad lane, it could reroute signals through spare groups. This improved reliability and yield. Results were strong. Adaptive D-skew and fast tracking improved eye width by 33 or 34%. Crosstalk cancellation reduced bit error rates from 1E-8 to less than 1E-16. UCIe 2.0 is not just fast, it's also practical and strong. UCIe 2.0 is not just a lab idea. It's already used in real products. TSMC and AMD shows a 3D UCIe links running at 32 gigabit per second per pin with 10.5 terabits per second per millimeter in nanometer. Cadence shows 5.27 terabits per second per millimeter using advanced packaging. Intel and Synopsys prove UCIe works between chips from different companies. If you design SerDes, mixed signal files, or chip collections, UCIe 2.0 is something you should know. For SerDes engineers, the focus is changing from signal equalization to clock stability and power saving. Instead of using CDR, we now use match delay clocking and per lane skew correction. For mixed signal designers, we build new receivers that don't need heavy clock recovery. For chip architects, we now focus on how to use space well, not just edge routing. As chiplets grow in use, UCIe 2.0 gives us a standard, power efficient, and scalable way to connect them. Here are summarized images showing you why UCIe 2.0 is important. It supports true 3D stacking with hybrid bonding. It reaches up to 10.5 terabits per second per millimeter bandwidth and uses very little power, 0.6 picojoule per bit, or 0.46 with clock gating. Unlike SerDes, which use heavy equalization, UCIe 3D uses bump limit design with a simple clocking and drivers. At ICC 2025, the 3nm test chip shows cluster repair, memory-based, and crosstalk reduction that lower bit error from 1E-8 to under 1E-16. Top companies like TSMC, AMD, Intel, Synopsys, and Cadence are already showing UCIe working across platforms. For analog and SerDes engineers, this is a big shift. Focus on power efficient, bump dense designs. For testing, real-time fast tracking and memory are now key. UCIe 2.0 is not a future idea. It's already shaping how we design high-speed chiplet systems. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback and please share your comments down below. Lastly, please share the video link with the people who may be benefiting from it.